So thank you everybody, and I would say good morning, or good afternoon, good evening, I guess. I'm Lars Goldman from Norway, and actually I'm located on a small island on the west coast of Norway, so we don't have any OTEC sort of environment here. It's too cold, I guess, and too small delta T. But I've been still an OTEC enthusiast for many years, and was around in the 90s also. Sorry. Yes, that's about me. I was around in the 90s also, so I'm sort of a veteran, I guess. I was somewhat active in the then OTEC Doha association. And I'm affiliated with Norwegian Institute for Water Research and also Runde Miljøsenter on the island, and then also I have some contracts with Tokyo University of Marine Science and Technology. And I've been happy to visit some OTEC sites like Imari, Saga, and Nela, Kona, and yeah, also of course Kumijima a couple of years ago. So the OTEC, of course, you know, most of you are well aware of the OTEC technology, so I don't spend much time on that in this presentation. It's of course base load can operate 24 hours, and it can also make a lot of useful byproduct, as Nadia actually pointed out. So the designs, my talk will more be about the open ocean OTEC, or the offshore OTEC. So there are many designs of this kind of floating OTEC. And it will, of course, need the cold water from down below, usually from maybe 800 meters and so, and then you have the exchangers and you make the electricity and so on. So, and then you have to discard the used water, which is in temperature between intake water and intake warm and intake cold. There are also other designs of OTEC actually, like the one from Rao and Bard 2018. They suggested, like others also did, to actually have a submerged condenser down in the cold water. That means you can have much smaller pipes. So you bring the working fluid down and back up again. So of course that's something that some people are looking at. And they also have other actually means of sequestering actually CO2 in a sort of mineral reaction. So they can also become net negative, I think, with their plant. We have done many designs also in Europe, and this is from the Tropos project. We designed a multi-purpose floating platform which had the use for harbor, for renewable energy, and aquaculture and so on. So we also designed into this 16 megawatt OTEC, closed cycle OTEC plant. So this is just an artist's drawing of the whole structure. The byproducts we already noted. There are so many byproducts we can make from besides the electricity from an OTEC plant. And one to the right, actually, which is a little bit pertaining to the discussion today, is CO2 dissolution. And 20 years ago, we designed that was a time when they say you can sequester CO2, CCS, sequester from industrial plants, then you transport it by ships and you inject it in the deep sea, let's say 1,000-meter depth. That was something we worked on together with United States, Japan, and Australia. But of course, it was more or less put on the shelf due to some concerns about the deep sea environment. That's a pH change and so on. But if we could combine that with an OTEC plant, that would actually stimulate the operation of the OTEC plant. You would have higher efficiency. And we have also OTEC and the fisheries and so on. You can use the nutrients from the deep water, and you have the algae production, zooplankton, and fish and so on, like you have onshore in Kumijima. So about CO2, you know the ocean holds large amounts of CO2. And the emissions we have from our activity and power plants, they end up in the air first, and then they go, a large part, and end up actually in the ocean. So it's actually, if you have an OTEC plant that will bring such some intermediate ocean water to near the surface. So the question is, what effect can this water being brought up cause for the CO2 system in the ocean, and also actually the ocean circulation? Will CO2 increase in the surface layer? If so, maybe it will force CO2 back into the atmosphere. We don't want that. Can the deep water cause ecological impacts in the upper layers? That's also a little bit connected to our scope today. And then can large-scale OTEC change ocean stratification and surface water temperature? Then, if that's so, what kind of mitigation can we talk about? So climate change and the global emissions, you know, that's a hot topic. So the emissions still increasing very much, and they lead to the increased CO2 concentration in the atmosphere climbing, and that leads to the global warming, as you see. So of course I think OTEC can play a role here to curb emissions and reduce global warming. We know, of course, the ocean has enormous carbon storage reservoir and also a large storage capacity. So the carbon stored in the ocean is about 44,000 gigatons, and that's not so, that's quite much compared to the annual emissions of maybe 35 gigatons. So then land has some fraction here stored in the biosphere, and the atmosphere has maybe around 700 gigatons. And if we see projections on the evolution on the emissions, the scenarios that IPCC put forward, the ocean, it's a little bit complicated in maybe the sketch, but the ocean will still absorb more CO2 than today, which you see on the left side here. But the fraction of the total will be less. So the atmosphere has to cope with more and more CO2. The exchange with the ocean will slow down and so on. So that is the big challenge, of course. So in the UN and the goal number 13, take urgent action to combat climate change and its impacts. That's, you know, it's very urgent. That I think it's the biggest job for scientists and engineers in STEM, as you know, science, technology, engineering, and mathematics. So STEM is an important field. So my talk will be much about the ocean, actually. So this is the global warming in the ocean, which is actually on the whole planet. You see the polar regions, especially north, they are experienced the highest warming. So our OTEC belt, that is more or less, it's not so much changes yet, but there is a slight heating in the surface. I looked at some vertical sections from the WOS Atlas, World Ocean Circulation Experiment, in the 90s and also later. So this is 3 sections, or 1 section from north to south in the Pacific, in the middle, in the central Pacific, from north to south. And north is on the right and south is on the left. So this is temperature, oxygen, and nitrate as an example. So this is when you go down to 1,000 meters, this is the kind of water quality you will have in the deep water intake. So traditionally we say maybe deep water is a little bit hypoxic, has a little bit lower oxygen than surface water. And And also it will have a usually high nutrient content. But you can still find regions which have the necessary delta T of 20 degrees, as we say, that we can find waters which do not have those issues, especially they can be lower in nutrients if that's what we want, than which is usually found. And I also looked a little bit on the Indian Ocean, on the CO2. The Pacific is on the top. Below is the vertical section of total CO2 in the Indian Ocean. And the trend is also you have more total CO2 in the deep water or in the intermediate waters. So when we pump up CO2, I mean deep water for OTEC, we actually will have transporting some extra CO2 towards the surface, and we don't want that to be released to the air. But of course we can still find locations elsewhere that doesn't have this high concentration in the deep water. So there is a lot of talking now, how can we help, or how can the ocean help us to enhance the CO2 uptake as part of what we talk about carbon dioxide removal from the atmosphere. So there is an interest in ocean-based carbon dioxide removal technologies. This is, I think, in most, at least continents, the EU has a high focus on it. And we are working on some EU projects that are, we call them ocean-based negative emission technologies. So they are many actually. They are ocean alkalinization to increase the capacity for storing CO2. You can have a fertilization. You add certain nutrients or trace elements to enhance phytoplankton production. Then you have tailored marine biomass production. Then you can dispose the biomass in the deep sea, so it will stay away from the system. And then we have artificial upwelling, enhanced upwelling, that is actually, this will be something that will be OTEC relevant here. And OTEC is not brought to the table so much yet, but I'm trying to bring also OTEC to the discussion table. These are a list of those ocean-based negative emission technologies, and I put an arrow to the right here where possibly OTEC can play a role. So that is typically artificial downwelling, not maybe so easy, but at least artificial upwelling is evident. And also OTEC can be used in ocean fertilization and direct CO2 removal from seawater, also combined with CCS, carbon capture and sequestration. So this enhanced upwelling, which actually could be undertaken, they only estimate you have a pipe, so you bring deep water up by some means. It could be solar powered pumps, or it could be, yes, any means, but of course OTEC already bring up this water. So the idea is, if this is engineered properly, you have upwelled waters creating, increased phytoplankton blooms, and then you have also zooplankton, etc. And this biological material will eventually sink out and into the deep water, where it will be mineralized and dissolved as CO2. So it sort of will remove CO2 from the air. This actually vertical flow could be used, we could use the perpetual salt fountain by Henry Stommel. He suggested already in 1956, if you put a vertical tube in the ocean, and it doesn't have too much insulation, you prime it, you bring cold water up, which is less saline than the surface water in the tropics. So then heating through the walls, the flow will, the inside water will be heated and lose buoyancy, gain buoyancy, so it will rise by itself. So this flow will go by itself, actually. You don't need any pumps. So perhaps they should take a new look on his concept. You could also actually have it go the opposite way if you want. There have been several projects with this kind of enhanced upwelling. One very known is the Sagami Bay experiments in Japan. And they built a plant. This is the photo show the floating part. And then they had a maybe 200 meter or 175 meter pipe going down. And the same principle was used, and they had nutrient-rich water in the deep. Then brought it up, and they could observe actually increased increased phytoplankton and zooplankton production in the upper layer. So it was actually has been demonstrated. So this is the global view of chlorophyll in the sea, and I think in the OTEC belt, as I say it, that you have some areas where you have a significant amount of phytoplankton in the upper in the surface, but also areas where you don't have so much. So that means actually OTEC could help to stimulate primary production in some areas, actually, if we really want it. The microscopic phytoplankton, they consume naturally huge amounts of CO2. It's on the order of magnitude of the human emissions, actually. And there have been some sort of modeling studies and say how will, let's say, increased surface temperature in the ocean due to global warming, will that hamper the primary production, or will it be enhanced? And but they expect global primary productivity to change with a warming climate. So it might go up in some places, down in others, but we don't have a good grip on how those will balance. So it's a little bit open question now among the scientists. So I guess OTEC and CO2, is it anything to worry about? I think it's maybe not a big issue, but it's something we should put forward as an argument to actually install OTEC, that OTEC can help us to remove CO2 from the air. Of course, OTEC will, by operating OTEC, you avoid fossil fuel emissions. So that is evidently adding positively to the budget. But here we talk about OTEC operation, sort of what is caused by the use of the deep water, especially, and redistribution of ocean water. Is that causing maybe some impacts we don't want? So this is actually conclusions from 1990, and already then they said CO2 released during OTEC plant construction is expected to be small compared to what is released over the lifetime of a fossil fuel plant. Of course, you need to spend some fuel, so to say, to construct the OTEC plant. That is same for any plant. So let's say OTEC systems that incorporate subsurface mixed discharge, like we talk about in the floating, especially OTEC, are expected to result in no long-term CO2 release. So that was their conclusions then. I guess we are more or less there still. Then there are some concerns, and some say OTEC on the big scale is, manipulation of the ocean. It's geoengineering. But I think, let's say OTEC plants today are way below 1 megawatt. The designs are maybe 10 or 100 folds more, but still not very huge plants. The global OTEC potential, I mean, that potential is really huge. But if you say realistically, some calculated that at least you can extract 7 terawatt without changing ocean circulation on a large scale. So we are around this, that we can claim, no, it doesn't change circulation. And this is a huge amount. It means like 70,000 100 megawatt plants. So the arguments and our arguments, it's a matter of scaling here. I think realistically OTEC will not disturb global ocean circulation. And then about the nutrients upwelling, OTEC represents a sort of enhanced upwelling, as we heard. And the nutrients are brought up to the what we call euphotic layer, where phytoplankton is growing. So then algae will start grow. Algae consume CO2. Algae die off and sinks to the deep water. So then CO2 in the surface is reduced and more atmospheric CO2 can enter the ocean. So that's sort of good news. Then OTEC and the cold water issue. Bringing cold water up is also someone concerned about the impact of having cold water brought up. Of course, the surface layer or subsurface layer will be somewhat cooled. But there is actually, relative to CO2, colder water means more capacity to absorb CO2. So actually, that cooling could also enhance the uptake of the ocean of atmospheric CO2. So that means OTEC will contribute to negative emissions. Additionally, a cooler ocean surface actually will hamper the generation of tropical storms. So OTEC in a sort of sustainable, renewable world, I think OTEC represents renewable energy with a large potential. It can replace the use of large amounts of fossil fuels. OTEC as a climate mitigation technology, possibly a net emission technology, must be communicated also in light of the United Nations Sustainable Development Goals. Suggested negative environmental aspects like eutrophication, water cooling, and deep water species entrainment should be addressed, of course, and mitigation measures found. Additional benefits of byproducts besides producing electricity should be further explored, and I suggest in a multidisciplinary context, not only by engineers. So that was my brief message. Thank you very much.